I've been asked to introduce our speaker today. I'd like to say good afternoon to everyone, and please join me in welcoming Professor Ilka Brunner, a leading voice in mathematical physics. In honor of her work establishing elegant bridges between quantum field theory, string theory, and modern mathematics, she was selected as the Kirk Fellow during her stay here at the Isaac Newton Institute. And we have the privilege of listening to her speak. She is a professor at the LMU in Munich, where she has worked for almost 2 decades. Before she was briefly at ETH in Zurich and at my own King's College, among a few other places that I won't bore you by listing. Her work has been influential in many ways. She has had, for example, an important influence developing the concept of non-invertible symmetry, which is a big character in this program that we're holding here at the Institute these several months. Tonight, she'll take us to the frontier where symmetry, space, and quantum phenomena meet. And so without further ado, I present to you Professor Brunner. Please take it away.
So thank you very much for this nice introduction, and I feel very honored to have received the Kirk Fellowship. It's connected to a stay of 5 weeks here at the Newton Institute. This is my 5th week, and I had a wonderful and inspiring time here in Cambridge. So let me start my talk. It's about the interface between physics and mathematics, and in particular, I would like to highlight the topic of topological quantum field theory, which was much discussed at the current workshop. So what will I do? So past decades, I was contemplating to write centuries, have seen a fruitful interplay between mathematics and physics. So I didn't write centuries because centuries ago, maybe mathematics and physics was the same and difficult to disentangle, and I want to disentangle it and then bring it together again. Okay, so topological quantum field theories, the main topic, provide a class of examples where we can connect geometry and algebra and also physics. Okay, so what I will do is to first say something about math and physics and how it's different and how it's similar, and then dwell on quantum field theory, like why it's complicated, what is the status of it, and how can it still mingle with mathematics despite its deficiencies, and then we will discuss a bit of topological quantum field theory, its definition, and the applications we have discussed here. Okay, please interrupt me at any time in case you have questions or so. Right, so let me start with physics. I'm a physicist, so it's maybe the natural point for me to start. And what would be its aim? Well, its aim is a description of nature. It's one of the natural sciences. It's based on experiments. And there are procedures how we gain knowledge in physics or in any natural science. So what do we do? Well, we collect some data, for example, from experiments or by looking at sample models or something like that. So we look at many things. Then ideally one finds some patterns, so one interprets results and tries to find origins of patterns. So that means we explain the patterns, and what it means is to make a model, so some theoretical model that is in agreement with all the data. So it should be not just any old model, but something that is predictive, So something that has, for example, few parameters so that we don't have to describe every sample or every experiment that we do by itself, but we want to summarize lots of data into one big theory ideally. Okay, so then what language do we need, do we use to describe our models? Well, ideally, or what has been successful, is to formulate the physical laws in the language of mathematics. Okay, so now I'm not a mathematician, but I try to summarize mathematics in a somewhat similar pattern. So what's mathematics about? Well, it's about understanding structures, and then one wants to find the right words for these structures, so to describe them. So one needs formulations in such a way that these things can be understood by others in a unique way. So I think the procedures are, or at least can be, maybe depending on the mathematicians, quite similar to what we do in physics. So what do we do? Well, we study big classes of examples that could be, but don't necessarily have to be inspired by physics or some other natural science. Okay, then one finds pattern, and then one tries to abstract from the concrete examples and to then compress knowledge in definitions. So one tries to make some definitions that then allow to prove theorems. And so what is at the heart of mathematics? Well, I would say rigorous arguments, so rigorous, precise arguments are needed. And then one needs kind of like good definitions. I would say that, for example, that should, again, summarize many classes of examples into one definition from which one can then prove a strong theorem rather than describing any example separately. Okay. So how can we relate the two? Well, there's physics and there's mathematics, and there is possibly some overlap and some common historical origin. But how do the two different things interact now? Well, physics can give inspiration for mathematics. It can, for example, act as some, I don't know, conjecture machine that may inspire mathematicians to formulate something precise and then by rigorous argument give proofs of the suggested conjectures. Then going the other way, mathematics is good to formulate physical laws, to put them in some concrete language. It's good to formulate the general principle of physics, and again, abstraction plays a role. Okay, so let's be more concrete and let's talk about quantum field theory. So in particular, I would like to talk about the standard model of elementary particle physics. So what do we want in physics? Well, we want to describe some fundamental physical laws of our universe. So that's what quantum field theory is about. So it describes elementary particles and the forces between them. So here is a table of elementary particles. So they are organized in this nice little table, and there are some basic constituents of matter, and there are exchange particles that are good for the forces between them. Okay, so this a priori looks like a zoo of particles and like some way to formulate interactions, but I would like to emphasize one point that is crucial in pretty much any entry in this table, and that's symmetries. So there are different kind of symmetries that enter in the description of elementary particle physics. So one may start with space-time symmetries. So when we say this is a fermion or something, or this is a boson, then we mean a certain property, so how a certain representation under space-time symmetries. Then there are these interactions that are mediated by gauge bosons, and underlying is the symmetry, the gauge symmetry. For the standard model, it's SU3 times SU2 times U1 that governs all the interactions of elementary particles. Okay, so here is more about quantum field theory. So that's the same slide I showed you before, where I was talking about physics generalities and what physics wants. So the aim is a description of nature, and we now elaborate a bit more on what it wants in the context of quantum field theory and elementary particle physics. Okay, description of nature is, in this sense, particles and forces. It's based on experiments. So what experiments do we have to explore the particles and forces? Well, we have accelerators where we shoot things. It depends on what accelerator, where we shoot things one upon another and then do some scattering experiments. So this is a picture from the CERN LHC accelerator. Okay, then we do our procedure. So we collect data, we find patterns and origins and explain patterns, and that is the thing that the standard model that I showed you does. So we make a model, the standard model, and it needs to be predictive. So this model is predictive. So, for example, it has very few input parameters, such as the particle masses and some other things. And then we have a machinery that we can use to make predictions. And indeed, the standard model in quantum field theory seems like a very good and successful theory in the sense that it's predictive with very high accuracy. However, it's incomplete. I drew a few dots here. I just want to hint that there are some phenomenological incompleteness. For example, it doesn't describe all the particles. We know that there is dark matter and dark energy outside, and there are various unsolved problems that go beyond the standard model, beyond the standard model physics. So I don't really want to go into this part, and also I have no solutions for it. That's maybe one reason not to be too explicit about it. But I would like to continue talking about the formulation of its physical laws in the language of mathematics. So here is something left to do. So let me be a bit more precise about this. So what should we discuss? So we should discuss what quantum field theory is. So what is it about? Or a slightly different question. I said before that the standard model is highly predictive and makes prediction with high accuracy. But how do we arrive at our predictions? How do we compute amplitudes, and how do we get physical quantities? Well, in the case of quantum field theories, there are many different ways how we may think to formulate our theories, so many different ways to think about this. One prescription is to formulate and evaluate certain diagrams that are subsequently summed up, so in a perturbation series. So here is some diagram that describes the interaction of two electrons there's a photon exchange. It's valid at recoupling this whole procedure, and it's a perturbative expansion. And it has been very successful in the computation of scattering processes. Let me briefly comment. I said there are many different ways to think about it. So there are other ways to think about quantum field theory. So one way is to formulate things on a lattice and then to regulate things there and to take a continuum limit. And yeah, since we will give a mathematical definition later, I don't want to describe all the different methods. I would like to, yes, describe a few shortcomings of the descriptions that we have so far. So one thing is that formulations are, at least if they are in, as I indicated on the previous slides, they are perturbative formulations, so there's a perturbation series. There's no clear or universal prescription how to go beyond perturbation theory and how to capture non-perturbative effects. Then there are a few things that can be quite inconvenient about the perturbation series that we can formulate or about QFT. Things don't necessarily converge, so series doesn't converge. And when we formulate stuff, there can be singularities. That means that there's a whole procedure to extract meaningful answers from our computations. So we need to regularize our answers and then get something that we can interpret. There are many different approaches, and that means that things may depend on the approach you take and aren't necessarily unique. Okay, then the traditional, so if we think the standard model or traditional approaches to QFT are typically about local operators. There's a need to extend and to include extended objects, as we have discussed, for example, in this workshop. Okay, so here are some shortcomings. What I would like to emphasize is that QFT as a whole is not rigorous and not yet mathematical. Nonetheless, there has been a lot of interaction between quantum field theory and mathematics. So quantum field theory has inspired many different branches of mathematics. I did already talk a little bit about group theory, and that is also something that should be familiar to you, or I think is familiar to many of you. So if we have symmetries such as the symmetries that govern the standard model, then group theory, our knowledge of groups and their structures, comes in handy to describe interactions or to describe the theory. But in recent years, there have been many other mathematical fields that interacted fruitfully with quantum field theory, despite the fact that it's not formulated rigorously. For example, and surprisingly, there's number theory that in particular made an appearance in the context of string theory, in the context of conformal field theory. So, for example, there are p-adic versions of string theory. Well, it depends maybe how far you want to extend the concept of being physical, but in a sense it's surprising that these number theoretic quantities show up in physical models that we can make, that we can describe. Okay, then fascinating is algebraic geometry and its cousin-derived geometry. So from a math point of view, these two differ. So this is about rings and geometry one can extract from rings, and this also includes differentials, or differentials are important here in derived geometry, and then it has close ties with physics, because in physics we often think about concepts that are well defined up to some differential of something. So this includes BRST invariance in gauge theories. It includes the BV formalism, Battalion-Wilkowski formalism, when we describe equations of motions and how to resolve them. And it may include models where there's an underlying supersymmetric model, so there's a supercharge, and we don't take immediately cohomology, but we look at things that are defined up to a differential of something. Okay, so I won't talk too much about this today, but still one can discover nice categories inside here, or be inspired to extract categories from there. And the main mathematical concept I would like to discuss today in connection with quantum field theory is category theory. And the motto is that it lets us generalize the concepts of group theory and symmetry that we are so much used to. Okay, so let me comment briefly why quantum field theory interacts so nicely with mathematics despite its not rigorous origins. So despite all the challenges that quantum field theory still faces, there are many interesting interactions with mathematics. So on the one hand side, mathematics may help to organize parts of the physics, even in real theories. So that's what I mean. Here I want to allude to the discussion of the standard model. So in this real standard model, we had certain concepts coming from group theory that helped us organize our theory. Then another way how quantum field theory and math may interact is via toy models. So while we may not be able to formulate a full-fledged quantum field theory rigorously, there can still be simplified models that capture parts of the physically relevant models that can be formulated rigorously. And then there's an interplay between these two ideas, namely toy models may in turn capture subsectors of real models. Right. So let me dwell again on the idea of quantum field theory and group theory. So groups play an important role in physics as they describe symmetries of physical systems. So we have learned that groups may act on classical fields, and if the Lagrangian describing the interactions is invariant, we say it's a symmetry. Then there's a machinery that we can crank, namely Noether's procedure tells us that there are conserved charges and currents in such situations. And then via quantization, we get representations of the group of describing the symmetries on a state space. Groups impose constraints, or symmetries, I should say, impose constraints. So we want to talk about correlation functions in the quantum field theories. And then the incarnation of the symmetry on the level of the correlation functions are the so-called mode identities. So symmetries provide powerful constraints on theories, on correlation functions, on spectra. And the recent insight is that symmetries do not need to originate from groups. There is a generalization, namely categories. Okay, so What can we say about mathematically well-defined models or mathematically well-defined toy models? So typically they have a high symmetry or solvable subsectors. And then we can solve we can use the constraints to solve them. So examples for this are conformal field series, in particular rational conformal field series in 2 dimensions. I should have added. Other examples are supersymmetric theories. For example, there can be solvable subsectors. There are famous results such as Seiberg-Witten theory, where supersymmetry, the power of supersymmetry was used to solve a subsector. Okay, also topological quantum field series can be rigorously formulated, and in this context of topological quantum field series, categories are everywhere. Okay, so now I would like to formulate topological quantum field series using categories. So this is due to work of Attia and Siegel, end of the 80s. A topological quantum field theory is formulated as a functor between categories. So now I really need to say what a category is. So we have said at the beginning that mathematicians try to define mathematical structures, and then they would like to prove some theorem about that structure. For example, a classification, so to make a list of all things, to make a list of all, I don't know what, complex semi-simple Lie algebras or something that one can classify. But before one addresses such a question, one should think about maps between the to be classified objects, because while we in physics easily say this is the same, mathematicians need some isomorphism and say these two things are isomorphic, so they have the same structure, the isomorphic structure. And then classify things, for example, up to these natural isomorphisms that you can formulate. So all of this is summarized in the idea of a category. So what is a category? It summarizes, so there is some object, so contains objects, and together with it the morphisms, so the maps between objects, and then there are some constraints, so there need to be compositions that are associative, and each object need to have a unit element as part of its endomorphism. A rather classical example are just finite dimensional vector spaces over C, or you can put any other field if you want. So let me show you this slide again and then put in the vector spaces. So the in the category of vector spaces, the objects are vector spaces, then the natural maps between them are linear maps. There's a composition of linear maps that is also associative, and there's an identity map for any vector space that we have in that category. The example exhibits more structure than just being a category. For example, it has a tensor product, so for any vector spaces V and W, we can take their tensor product, and then it's again a vector space. This is called monoidal structure, and there is also a monoidal unit. So if I take the tensor product of the vector space with the monoidal unit, I get back the vector space. So this is isomorphic, in fact. And the monoidal unit in the case of vector spaces is just the field. Okay, so that's what a category is. So now we need to define our topological quantum field theory, and it's a functor between categories. So just as for vector spaces, we have vector spaces and linear maps between them. We can now crank this wheel and look at categories and natural maps between them, and they are called functors. So we have discussed the category of vector spaces, and to formulate a quantum field theory, we need another category that will take the role of space-time. So that's a Bordism category. What is the Bordism category? Well, the object of the Bordism category are d-1 dimensional compact manifolds, and the morphisms are Bordisms. So d-dimensional manifolds whose boundary is E1 disjoint union E2 if it's a morphism between E1 and E2. The composition is gluing. One may add extra data and one such as orientation, spin structures, whatever. And this is a bit sketchy. One should discuss this gluing and many other things in more detail, but I hope that for the purpose of a colloquium style talk, it's enough to appeal to your intuition. Okay, let me discuss the situation, what happens when d is 1 and d-1 is 0. So that means the objects, they are d-1 dimensional compact manifolds. So in that case, there would be points and disjoint union of points. If we put an orientation, we would label the points plus and minus. And the morphisms are lines that connect the points. So for example, this one and that one. There's a monoidal structure, which is this disjoint union, and the monoidal unit is the empty set. So this thing is to be read as a map from plus point, disjoint union minus point to the empty set, and this the other way. Okay. Here is another example, one dimension higher. So one-dimensional objects, two-dimensional morphisms. So the objects are disjoint unions of circles, and the morphisms are Bordisms. So here is a map or Bordism between two circles and one circle. It looks like a pair of pants. I drew it here upside down. This is, of course, the same Bordism in a sense, but I'm reading these pictures bottom to top. So I read this from disjoint unions of two circle to one circle, and this the other way. And here are a cap and a cup from which you can, for example, glue a sphere if you compose them. Okay, so now I would like to put the two categories that I have presented into one category. So I would like to formulate a Bordism category that has two-dimensional things, one-dimensional things, and zero-dimensional things. So points, lines, and two-dimensional surfaces. So what do I mean by things? Well, I again would like to talk about points as objects. So there are points that are objects, and there are one morphisms connecting the points that were the morphisms of the Bordism category I presented to you before. But now I would like to regard the two-dimensional surfaces as coming from sweeping out two-dimensional surfaces between one-dimensional corners. So let's look at this piece of surface as a map from that one, this one morphism, so this line, disjoint union with that line to this pair of lines. So this piece is just a piece of surface that connects different of these different arcs and straight lines in one dimension lower. This thing connects the empty set to a circle, and I view this circle as being split up into two such arcs, and then this is a morphism between the empty set and the composition of these two arcs, gluing them together in the other way compared to this one. So here I just joined the arcs, putting this one there, and then looked at the map from that disjoint union to these lines, and here I glued together two arcs to make a circle. Okay, and then there are also these opposite guys. Wonderful. Are there any questions about this? Okay. If not, let me say where we were again. So a few slides ago, I kind of tried to advertise that what the TQFT should do, or what should the quantum field theory do? Well, it should associate something to a piece of space-time. And the space-time part is formalized in this Buddhism part, and then it should map to some other algebraic structure, for example, the category of vector spaces. So I indicated at the previous slides that geometrically one may want to think about higher categories, so where I don't just have objects and morphisms, but where the morphisms also form a category. And I would now like to find higher categories that can be suitable target categories if I want to think about more the geometric categories in a higher categorical sense. So what should these higher categories be? Well, they should be, or what do we want? We want that they are somehow physically motivated. That's one piece on our wish list, and the other piece on our wish list is that they should help us to rethink symmetries, because we wanted to see how symmetries are not only modeled by groups, but that there can be more abstract mathematical structures doing that. Okay. So here is a way how physics and higher categories come together. It comes together by considering extended higher dimensional objects as part of our physical theories. So consider some field theory, theory 1, and some other field theory, theory 2, and now we want to connect them by a codimension 1 piece. This is called a defect, or domain wall, and it connects two a priori different bulk theories. For example, if you like to specify physical theories by an action, you may think to just specify some extra degrees of freedom on this codimension 1 piece, and to formulate an action for these degrees of freedom among themselves, and also how they couple to the fields that come from the bulk theory. You may also think about these such defects as gluing conditions for bulk fields. That's maybe similar to boundary conditions that form a special case of this scenario. So just think that there's nothing here, so no theory 1, just theory 2, and then this defect gives a boundary condition for theory 2, and then what you need to do in physics is to specify boundary conditions for the fields of theory 2. And if you have a non-trivial theory 1, it means you have to impose non-trivial gluing conditions across this defect. Another special case, apart from boundary conditions, is again symmetry defect. So let me come back to the situation where we have a symmetry group. So let's say theory 1 and 2 are the same, and there is a symmetry group for that theory. Then we may use the symmetry of the theory to impose gluing conditions. Okay. There is a composition of defects, namely merging, in a real quantum field theory with actual, so in a quantum field theory that is not topological, this merging is a complicated operation that is difficult to compute even in the simplest or in free theories. But in topological theories, you can think about just merging these surfaces and getting a new defect that I denote D1 tensor D2. So it's just the defect that you get if you throw these defects one on top of the other. Doing so, you squeeze in any bulk fields that are sitting in between these defects, and they become defect fields on this merged objects. Right. If there is a symmetry group G, we can now reformulate what we know about symmetries mediated by groups in the new categorical language. So let's assume that we use our symmetry to glue bulk fields to their symmetry transformed versions. Then, if we do this merging, so let's say we use a group element G on this defect and H on that defect, then if we merge these two defects, the group elements will compose. So the group law that we know about becomes part of the defect story. In particular, there is an element, a unit element in G, and there is a defect that corresponds to the unit element, and it's just a defect that does nothing, so has trivial gluing conditions, and that Andreas called in his talk yesterday the no-brainer. So in particular, such defect exists in any QFT, not just in topological ones. Okay, so what we see here is that ordinary symmetries can be reformulated in terms of defects. And now dropping invertibility, or that this defect comes from a group, we can look at a more general class of defects that can serve as symmetries in a similar way like groups can do. Okay, so now I said I wanted to drop some assumptions about groups. But before I can really do that, it's in a sense good to also talk about dropping other assumptions. So the group elements were related to codimension 1 defects, and it's then natural to also admit defects of other codimensions. So for example, here I drew a codimension 1 domain wall and on it a line operator. So it's codimension 2, and you can think about defects of any codimension. So here there is also a point defect added, and in general you can think about any dimension. You have this invisible gluing condition for any dimension and impose trivial gluing conditions on fields. For example, you can also just talk about line operators in a bulk by saying that they are line operators on an invisible surface defects. So also they are higher morphisms between one morphisms. Okay. So now we have formulated another category, a defect category. So the objects are theories, the morphisms are codimension 1 defects, the composition is merging two morphisms are codimension, two defects, and so on. But let me come back to like the initial questions. So now we have a nice category, but what was it that we actually wanted to do? Well, I think we wanted to do two things. One thing is to find target categories for higher Bordism categories. So by higher Bordism categories, I mean the category that talks about point, line, surfaces, and so on all at once. So we need some structure that mimics this higher Bordism structure that we have seen. And the other thing is that we wanted to rethink about symmetries. So let me go over these two ideas in turn. So here I show you again the Bordism category 210, where we think about points and lines and surfaces all at once, namely about the lines connecting the points and about surfaces connecting the lines in this way. But now I want to put emphasis on this target category. So we want to map this to something. And the map this to something is again a category, and the category I have advertised to you, I think, is the category of defects. The category of defects had theories as objects. So we want to map points to theories. The category of defects had codimension 1 defects as one morphisms. And so we want to map this little arc to a one morphism in the category of defects. So now this arc is just one morphism, and in the category of defects we have tons of one morphisms. So we need to ask which defect should we map this little arc to? And the answer is that this is a variant of the invisible defect. So if you think about, so I'm again copying this from Andreas, so let's think about the theory, a theory living on this piece of paper, and we draw an invisible line here, so that's the no-brainer or invisible defect, and then we fold things along this invisible line. Then we have obtained a boundary from the invisible defect, and this whole thing is called the folding trick. So let's look at this once more. So I would like to map, so this can be viewed as a bending line, which is an identity morphism in the geometric category. So bending it over, and so we wanted to map in the target category to a bend over identity defect. And then this also, and then, yeah, these things in a, yeah, way. So this is kind of the folding trick, and this is the folding trick on steroids and even higher dimensions. So this is summarized again here. So what are images of the pictures I showed you before in the target category? Well, we map points to theories, and we map these little elbow dents that I showed you to defects obtained from invisible defects by the folding trick. And then mathematically, this presence of this folding trick and association means that an object, so a theory in the category, needs to be dualizable. So I need to be able to fold things over in the way I showed. In particular, so if I want to do this multiple times and also in the higher dimensions, objects need to be fully dualizable, so dualizable several times. Then if one has that, then one has specified a functor completely, because now to any Bordism one can associate, so any Bordism can be cut up into these building blocks. I'll show an example on the next slide, and then we can evaluate the functor by using the gluing, which is the composition. So here's an example. So this is a torus cut up into building blocks that I showed on the previous slide. So there's this cup and this cap, and then there's this saddle and inverted saddle and some unit morphisms. And then we read this diagram as in terms of the building blocks. So these units correspond to those two pieces, and then the saddles and inverted saddles corresponded to some folded version of identity defects that are written in this formula here. I don't want to detail this out further. I just want to mention that by cutting up, one can convert such a picture into a concrete formula and to be evaluated in a target category. So now we only put identity defects and their variants in our game, and we can now put the other defects back in as well and evaluate any such diagram. So this is a piece of Bodism with various defects drawn in and various local fields drawn in the bulk and on defects, and if our category is nice enough, then we can just take these diagrams and it translates into a computation prescription via graphical calculus developed by these people. Okay. So my point one was to develop simple QFT models that are mathematically well defined using categories and using categories of defects, and this is as far as I want to go about it. My point two that we wanted to do with the higher category coming from defect was to use them to rethink symmetries. So we still have to rethink symmetries. I indicated in a few places how we want to do that. Okay, I keep confusing the pointer with the forward. Okay, right. So what did we see so far? Well, ordinary symmetries originating from groups can be reformulated in terms of defects. So codimension 1 defects with gluing conditions coming from the group were just a defect realization of the ordinary symmetry. Then defects can act on other operators or so because we can wrap them around other operators. And now the point is that this can be done in any quantum field theory, not just topological ones, as long as the defects are topological. So I can wrap a defect around an operator insertion if I can move the defect freely. So as long as my defect is topological, I can do this merging around, wrapping around. The question remains, however, like, okay, so now I have defects, I can wrap them around stuff just like I can do for symmetry defects, but in what sense is it a symmetry of the theory? So one manifestation of symmetry is that they give mode identities between correlation functions. So we want to compute correlation functions and see how symmetries constrain them. And I think, so I stole a picture from an old paper from 2001 that discusses how defects give rise to non-trivial relations between correlators, even if they don't originate from groups. So this is pictured here. So the model is the Ising model. You can read this as Ising model fields. So if you know the Ising model, if not, it doesn't matter. It's about a 4-point function with 4 operator insertions. How do we get an equality between this 4-point function and some other 4-point function that makes use of defects? where we insert a little loop of some defect line here that is not necessarily, or in this case, it is not a group-like defect, and then we pull this defect across these insertions. So if the defect is not group-like, it will drag, when we pull it over, it will drag behind it some other non-trivial line defects and make these operators sit at the end of it. So that makes these operators disorder operators or generalizations thereof. Okay. So that's very nice. So in a sense, we have a representation, a manifestation of some symmetry on concrete theories. So that is, I think, comparable to talking about a representation of a group in a concrete theory. But what math then does or likes to do is to talk more, to again add one more level of abstraction, namely to separate the abstract symmetry from the actual realization with the help of defects in a theory. So we don't just want to talk about the defects in a theory, but we would like some more abstract notion that separates the symmetry concept from the concrete realization in a field theory. So there is a very nice idea by Friedmore and Telemann recently that does that, and that marries the two ideas I've been presenting, namely the categorical formulation of TQFT on the one side and physical realizations of defects inside physical theories on the other side. So what does it do? Well, it talks about, so for a d-dimensional physical theory, that's in this picture here, it talks about a d+1 dimensional TQFT, topological quantum field theory, that describes the categorical symmetries, or all symmetries, in fact, of the physical theory. So we pull out all this topological data and how that there are these higher dimensional things that can be wrapped, and we package them into a higher dimensional field theory that contains all the symmetry stuff. And then there is, so there's this d+1 dimensional higher dimensional symmetry that describes this higher dimensional TQFT that describes all the symmetries of this physical theory. And to do this, we also need to specify a topological boundary so that the symmetry data is packaged in a topological boundary for a topological quantum field theory. And then this is the piece that acts, that captures our symmetries. Okay. So I should finish. So let me wrap up. So here's the slide I would like to come back to. So at the beginning I talked about the relation between physics and mathematics, and that physics gives some inspiration to mathematics, and mathematics does abstraction and formulation of physical laws. And I kind of try to advertise that we have generalized way about thinking about symmetries inside quantum field theories. And so the concrete inspiration I would like to draw on this arrow is that we are inspired by quantum field theory and by defects and the formulation of defects and the generalization of symmetry concepts they imply. And then on this arrow I would like to draw. So we now take some abstraction, and we would like to think about functorial formulations of TQFT, or maybe more general QFT as well. And we would like to think about categorical symmetries and about abstract symmetry data that acts on concrete quantum field theories. Okay, so here are a few further conclusions. So Topological quantum field theory provides simple models for QFTs, and they result in computable diagrams that are also well defined. So they are nice toy models, but also non-topological QFT may have topological subsectors. In particular, these topological quantum field theory help us understand the symmetries of other quantum field theories. In this whole formulations, I didn't emphasize this so much, but at the heart of all of this is consistency, and how consistency helps us to constrain possible theories, amplitudes, and symmetries. And this is at the heart of many recent developments in physics. Okay, so at this workshop we have seen many talks about rethinking symmetries and its applications in physics. This includes constraining renormalization group flows, constraining correlation functions, as I also indicated, and also classifying phases in condensed matter systems. So thanks a lot. Thank you.
Questions for Professor Brunner? Yeah, Andy.
You know any examples where experiments have revealed some new categorical symmetries that were not groups? Or vice versa, where some categorical symmetry was proposed and then...
Yeah, so I didn't talk about the more standard model stuff because I'm not aware of like anything non-trivial in the particle context, particle theory context, but it seems that in the condensed matter systems, the classification of phases seems to be, the categorical symmetries seem to be quite relevant for topological phases and things like that they can see.
Okay. The stuff they've seen already, they can now interpret it in terms
Well, I don't know how impressive this is, but that's or how great these experiments are, but I have heard about such things in talks by them. I don't know if as any of you, for example, gave the tutorial for the phases lectures.
I think there are these experimental realizations in quantum simulators of non-real quantum doubles.
Yeah.
So these are these non-vertical symmetries,
Yeah.
besides that.
No.
More questions? I have one. Listening to you talk, you have all these sort of topological theories with lines and surfaces and so forth, and I'm sort of struck by a similarity like string theory, which has strings and d-branes and so forth. Do you see a connection between the two? Is there a way to revisit string theory in light of all these developments, or?
Yes, so I mean, d-branes are defects from a target perspective, and then of course they are not topological, but you can twist it, for example. So I don't know, so recently so by work of Costello, for example, he talked about how to twist supergravity theories topologically, and then you can put branes in such backgrounds, and in this way engineer using string theory or ideas from string theories. You can engineer topological quantum field theories by using, for example, Hanani-Witten style brane constructions and put them in a deformed supergravity background.
Other questions? If not, let's thank Professor.